Hello, today we are going to be talking about radians, which are a way of measuring angles, the arc length of circles, and the area of sectors. To begin with, radians are another way of measuring angles. We're already familiar with the way of measuring angles that we've used since primary school, which is degrees. So we know that there are 360 degrees in a full rotation, or 360 degrees in a circle. By definition, we say that there are 2 pi radians in 360 degrees. So radians go from 0 to 2 pi just the same way as degrees go from 0 to 360. And we define one full rotation. So starting at one point and rotating all the way back around to the same point as being 2 pi radians. Now, this way of measuring angles is useful because it tends to simplify certain types of calculations. Pi often gets carried around in stuff involving rotations, and the fact that radians are measured in pi often simplifies the problem. So, in practice, this is the key fact that we must have in mind for being able to work with radians and degrees and the relationship between them. If we can remember this rule here, that 2 pi radians, rad for radians, is equal to 360 degrees. If we can keep that in our minds, then we can do any conversion we need to between radians and degrees. Let's put this into practice. If 2 pi radians is equal to 360 degrees, what would 1 radian be in degrees? So this is just a ratios type question, a ratio and proportion type question like we've handled for years. So if 2 pi of something is equal to 360 of something else, divide both sides by 2 pi, and 1 radian must be equal to 2 into 360 goes 180 times, so it's 180 all over pi. So if I wanted to know what 1 radian was in degrees, I would put into my calculator 180 divided by pi. And this initial relationship is what tells me what I would need to do. Now, usually we won't need to just deal with 1 radian, we'll need to deal with some complicated angle. Take, for instance, if we wanted to know what pi all over 2 radians was. Radian angles will very often have pi involved in them. So what would pi over 2 radians be? Well, if I know what 1 radian is, I've figured out that 1 radian is 180 divided by pi degrees. So if I wanted to know what pi over 2 radians would be, I would multiply both sides by pi over 2. Again, this is just a ratio and proportion type deal. And this is how we convert between radians and degrees. So we knew what 1 radian was, so now pi over 2 radians is going to equal, we divide these in and we end up with 90 degrees. So the pi's divide out to 1, and 180 divided by 2 is 90 degrees. So 90 degrees, rotating through 90 degrees here, 90 degrees would be the same as pi over 2 radians. So that's how we would go if we wanted to find radians in degrees. We are going to use this relationship here. Likewise, if we wanted it to go the other way, if we wanted to know what 60 degrees was, say we wanted to know what 60 degrees was in radians, we want to know 60 degrees in radians. We know 360 degrees is equal to 2 pi radians. Divide both sides by 360 to find out what 1 degree is in radians. So 1 degree is equal to pi over 180 radians. We want to know what 60 degrees is, so multiply by 60. And we will get that 60 degrees would be equal to 60 divided by 180 is 3. So we end up, or a third. So we end up with pi over 3, or a third of pi radians. So that's how we do our conversions between radians and degrees. So our 90 degrees down here would be the same as pi over 2. It would be the same as pi over 2 radians, and 60 degrees would be pi over 3 radians. And this relationship is how we work that out. Now, we'll start to see why we would bother with radians when we start to look at the formulas for the length of an arc of a circle and the area of a sector. So a sector is like a pie slice taken out, or a cake slice taken out of a circle, and the arc length is part of the circumference of the circle. So we go around through a particular angle of theta. Theta is just a letter we use for angles. There's no significance to the fact that it's a Greek letter versus an English letter. It's just a letter that gets used a lot for angles in Leaving Cert. If we go through a particular number of degrees around our circle, what length have we gone around on the circumference? That's what the arc length L is. And the formulas that we're going to use here, both the degrees version and the radians version, are on page 9 in your log tables. So our arc length formula is fairly sensibly in degrees. If theta is in degrees, theta or theta is in degrees, we'd be looking for what fraction of our circle have we gone around. So that would be theta all over 360. What fraction of the circle have we gone around, multiplied by the circumference of the whole circle. So if we'd gone through 90 degrees, we'd have gone a quarter of the way around the circle, so we'd get a quarter of our circumference. Let's put this into practice in a question. If I said that OR was 4 centimeters, so I have the radius of my circle is 4 centimeters, and the angle I'll start off with being in degrees, we'll say is 30 degrees. So let's sub that into my formula and see what arc length I get. What length around here do I get? So I have L is equal to 30 out of 360. What fraction of the circle have I gone around? Times 2 pi times 4 for my radius. When I work that out, I've gone a 1/12 of the way around my circle. And when I work that through, I get 2 pi all over 3. And I don't forget that I was given centimeters for my question, so it's centimeters. So what fraction of my circumference have I gone around? Fairly straightforward. Now, this is if we're dealing with degrees. What fraction of the circle have we gone around? Let's think about this formula if we were dealing with radians. So L is equal to theta in radians all over what? Well, this time the total is 2 pi. So it would be times 2 pi, or I have 2 pi divided by 2 pi. So I'm just left with theta times or. And this is the formula that is in your log tables. If theta, the angle, is given in radians, the arc length is just theta times r, a much simpler looking formula than the one we were dealing with already. So to convert our angle of 30 degrees into radians, you will find that you get 30 degrees is equal to pi all over 6 radians. So if theta is in radians, I'm able to use this much nicer formula, which again is on page 9 in your tables. And we sub in, and we should find we get exactly the same answer. So pi over 6 for our angle, pi over 6 radians for our angle, and we're still using 4 centimeters for our radius. So we get 4 pi all over 6, which simplifies common factor of 2 down to 2 pi all over 3 centimeters. So that's how we can use our arc length formulas in either degrees or radians, and you can see why radians gives us a nicer formula. Now let's do the same thing with the area of a sector. We're effectively just looking for what fraction of the circle have we covered over. So again, if we take r is equal to 4 centimeters and theta is equal to 30 degrees, subbing into our formula, what fraction of our circle's area have we taken up? It's going to be 30 all over 360, so a 1/12 of our circle. When we sub that in, we get 4 pi all over 3 centimeters squared, because it's an area we are dealing with. And if we look at our area formula and think about what would happen if we were dealing with radians, theta in radians would be all over 2 pi times pi r squared. We recognize we can divide out the pi, and we are left with a half theta in radians r squared, which is again a nicer, simpler formula than what we had before. And again, our r is going to be 4 centimeters, and our theta, if we do our conversion, is going to end up being pi all over 6 radians. Because we're in radians, we can use this nicer formula. The area of our circle is going to be, a sector I should say, is going to be a half pi over 6 on 4 squared. And that simplifies down to 4 pi all over 3 centimeters squared. So they give you the same answer. The radian versions are a little bit neater. When we do more advanced trigonometry, we will often deal with radian measures of angles, because even though we get into fractions, we end up with functions that work nicer. So a lot of more advanced mathematics comes in assuming that we are working with radians, and we need to be able to convert between them both on our calculators and also using our relationship 2 pi radians is equal to 360 degrees. And these formulas and our conversion to radians and degrees